Hey everybody, Mr. G again. Welcome back. Today what we're going to be doing is part A of lab number 3 for the Tech 159 Electronic Devices and Circuits course. So what we're going to be doing in part A is we're going to be examining our transformer. So this transformer is a center tap transformer. 120 volts coming into the transformer through our AC plug, and then I've got these three little wires coming out on the secondary side. So we've got yellow to red, we will call that secondary winding A, and blue to red, we'll call that secondary winding B, and then we'll call blue to yellow the full secondary winding. So the first thing it's going to ask us to do is measure the resistance of each of the windings. So what we're going to do is this plug is connected directly to the primary side. So what I'm going to do is I am going to just measure the resistance. So the resistance 46.5 ohms. Let's move this probe out of there so you can see. 46.5 ohms. So that is the resistance on the primary side of that transformer. Now we're going to look at the resistance of the secondary. So without the transformer plugged in, resistance of the secondary winding A, so we had said that that's going to be red to yellow, and it doesn't make a difference. 1 ohm. 1 ohm, and now we're going to go on secondary B, which is going to be red to blue, 1.8, 1.9 ohms. And now what we're going to do is we are going to go for the full secondary yellow to blue, so 2.5, 2.6 ohms. So what that tells me, other than the meter is not perfectly accurate, what that tells me is that on this transformer it's been used and abused a little bit. So the windings from winding B, so that would be from the red to the blue, should be identical in resistance to red to yellow. Well, what this tells me is because they are a little bit different, so the resistance here is again about 1.8, and the resistance here was somewhere around 1 ohm. What this tells me is that one side of this transformer of the windings have been abused a little bit. So what does this whole thing look like? Well, here is our transformer schematic that we have. So this transformer is 120 volts in. We got a center tapped secondary, so that means with 120 volts coming in, we should have 6.3 volts coming out here, 6.3 volts coming out here. These are all RMS measurements. So 120 volts coming in, theoretically we should get 6.3 and 6.3. So what we're going to do is we are going to see if this is indeed the case. So we're going to connect the primary winding of the transformer and plug it right into the wall. So I'm going to disconnect this from the meter here. I'm going to plug my plug into the wall. So now there's 120 volts coming into my transformer. Now, just to make sure that we do have 120 volts and that our hydro system here in Ontario is having a good day, we will see how close we actually are to 120 volts. So this is AC. So I've set my meter up to measure voltage on AC, and I've changed to these probes because what I'm going to do is I have this extra plug plugged in exactly where I have the transformer plugged into the wall. So now I'm going to basically just stick these probes into this plug and see that we are having a good day. 119.5 volts. So 119.5 volts of RMS. That's what's going into the primary side. And now what we're going to do is we'll take a look and see what is coming out of the secondary side. So we're going to do this in two different steps. One, we're going to look at it on the scope, and we're going to measure peak-to-peak values on the scope, and therefore you can calculate the RMS value from that. Then we're going to use the voltmeter and measure the RMS values, and then you can calculate the peak-to-peak. Okay, so far we've got our resistance windings, and we've got voltage coming in. So now just a little note. Why is it that the resistance measurements are important in a transformer? The resistances themselves don't really affect how much voltage goes from one coil to the other. So the inductance, how much mutual inductance transfers the flux from the primary into the secondary. But what it does affect is the efficiency of the transformer itself. So every time you have resistance in windings and you put current through those resistances, we get heat. Heat is energy loss. Energy loss is a decrease in efficiency. So the higher the resistance of the wiring inside the transformer, typically we end up with more losses due to heat. Therefore, a lower efficiency of that transformer. So what we're going to do now, since I've got the voltmeter all hooked up, AC, this is reading an RMS value, I'm going to do this part here. I'm going to measure the voltages coming into the secondary. So secondary A, secondary B, and then the full secondary. So this is going to be my RMS measured, since I already have my voltmeter sitting right here. So let's go to A. So secondary A has an RMS value of approximately 7.0 or 7.15 volts. 7.15 volts. Now in theory, when I do the same reading on the other side, I should get the same. So 7.17 volts. So theoretically they are pretty identical. So we've got voltage on secondary A at 7.15, secondary B 7.17. Theoretically it's supposed to be 6.3. But what we have here is an unloaded transformer. If we were to start using this transformer and we were to actually start drawing current from this transformer, you will see that the values at the output drop down to what they're actually rated for. So this is basically open loop. So we have a little bit higher voltage coming out of an unloaded transformer than if we actually were using the transformer in a circuit. So that makes up a little bit of the difference. So what we're going to do now is I'm going to measure the total secondary. So here's the voltage, the dVm, total secondary 14.39 volts. So again, A is 7.17, 7.16. B is the same. And then add them together and you end up with the total 14.3. So that all makes sense. Okay. So now what we're going to do is we're going to put that onto the scope and see what that looks like as a peak-to-peak measurement. So from that part of the measurement, you can actually calculate your value of peak-to-peak. So from the beginning of this course, you've got your AC circuits course. From the end of Tech 101, you should be familiar with what is RMS values and how you calculate RMS values and turn them into peak values and vice versa. So now what we're going to do is we're going to measure the peak-to-peak value. So I've got my scope here, got the probe, and what we're going to do is we're going to go secondary A, peak-to-peak value. And we're going to make it bigger. Drop the trigger down so it stays in place. That's too big for our scope. So what we're going to do, back it off just a little bit. Let me see if I can move this out of here for you. There we go. And we will make it a little bit bigger. So there is our waveform coming off of secondary A. And we will measure. So the period is 16.6 milliseconds. Frequency, since we are in Canada, frequency in Canada of electricity coming from the wall is 60 hertz. And our peak-to-peak value is 20.4 volts. So 20.4 is our peak-to-peak value. Not our peak value, our peak-to-peak value. So what we're going to do now is we're going to take a look at secondary B. Peak-to-peak values, 20.4, frequency and period are the same. Okay, so again, the peak-to-peak value is 20.4 volts. Frequency in Canada, 60 hertz, which translates to a period of approximately 16.6 milliseconds. So that's what we're reading here. So if we looked on the scope, we have 5 volts per division. So we got 1 division, 2 divisions, 3 divisions, 4 divisions. Okay, so 4 divisions, 5 volts each division. Therefore, peak to peak is 20 volts. And when we look at the exact measurement, it's actually 20.4 volts. Now what we're going to do is I will go across the full secondary. So on the full secondary, it's giving me a peak-to-peak of approximately 40.4 volts, same frequency, same period. So I'm going to see if I can just bring this on the scope a little bit more here. Oh, sorry. There we go. So 40.4 volts peak to peak. So 40.4 volts peak to peak. So now when we're looking at this, we have total secondary peak to peak 40.4. Secondary B was 20.4. Secondary A 20.4. You can now take those peak to peak measurements and turn it into an RMS value. So one more time. So secondary A, peak to peak, 20.4, secondary B, 20.4, and then across the full secondary, 40.4. Okay, so we've got those measurements. These you can calculate. We took those measurements, and those ones you can calculate. Using the information gathered in step 3, calculate the following. So you've got 3 calculations that you can do based on the measurements that we just took. Okay, so the voltages coming into the primary and the voltages coming out of the secondary. Okay, so you know what the voltage is coming in. We know what the voltage coming out at A, out at B, and out at the total are. And you can figure out what the actual turns ratio is for this particular transformer. So that concludes the live version of part A. You will then move on to part B of this lab, and you will move to multi-sim, where in multi-sim you're going to simulate this transformer. And you're going to use this transformer right there. You're going to use this transformer in a half wave and then a full wave rectifier circuit. Okay, so this transformer becomes simulated now for part B and for part C. So that concludes, again, part A of lab number 3 for Tech 150, Electronic Devices and Circuits. So that has to do with our real-life transformer and some basic measurements. So I hope that helps. Everybody stay safe, and we'll see you again next time. Have a great day.